All right, we've been working in section 9.1, and we had, as a couple of you mentioned, one more example problem we're going to take a look at. So let me flip to where we were. That looks like it. So we're going to talk about determining whether this sequence is monotonic and or bounded, and then to confirm it graphically. And I think we spoke actually briefly at the end of class last time about what the graph's expectation was. And that it looked like a rational, it is a rational function. It has that sort of a graph to it. All right, so we're going to take a look at determining whether this sequence is monotonic and or bounded. Let me remind you real quick that when we defined something being monotonic, it was all based on this series of increasing or decreasing terms, right? So what we're going to actually take a look at is what happens when we compare this term, a sub n, to the next term, which would be a sub n plus 1. Sound good? Okay. Sorry, I forgot my stylus for a second. All right, so we know a sub n. Let's actually write down what a sub n plus 1 would look like. So we're going to replace all of our n's with n plus 1. So these are where previously I had n and now I have n plus 1 in those slots. So how will my numerator simplify? N, and the denominator will be n plus 2, right? I'm going to kind of do, it's not really a trick, but it's one of those, tricks of the trade kind of things that you wouldn't necessarily have known about, so I'm going to show you. You guys ready for that? Okay. We want to compare these two, right? We want to compare the a sub n we started with the a sub n plus 1 that we've now created. The way we're going to do that is we're going to compare them by forming a ratio of them, okay? So let's take a look. We're going to write down a sub n plus 1, our new term, over a sub n. So the a sub n plus 1 was the n over n plus 2. And the a sub n that we started with was n minus 1 over n plus 1. Complex fractions, it's algebra, right? Our favorite. Algebra's good. How can I simplify this so that it's not so messy looking? You bet. We're going to take the denominator and we'll flip it. Okay, did I get it flipped right? I think so. So here's what we have. All good so far. All right, let's simplify. Well, not necessarily simplify, but let's go ahead and expand, clean up the numerator by multiplying through it. And I will have n squared plus n over n squared plus n minus 2. Okay, all good so far, right? Just some algebra going on. All right. Here's one of those tricks again. Like I said, here's the first trick. We're going to actually write this in a ratio form and see what happens. Here's the next trick. It'd be really nice if some of these factors that I just eliminated when I multiplied through had sort of been able to cancel out. That'd been really friendly, wouldn't it? In fact, when we flipped that fraction, we were all probably kind of hoping that would happen, and it just didn't on this particular one. So we're going to kind of, try to make that happen and get something to cancel out. In particular, here's what we're going to do, and I'll change colors so that you can make sure you're seeing it really happen as it's happening. What we're going to do is we're going to actually put minus 2 on top. I'm going to make it look exactly like the bottom. That looks pretty good, right? But undoubtedly, I've got a frown right here. I changed something. I can't just put minus 2 on the top, can I? No, I can't do that. So what I'm going to do to make up for it is I'm going to put that same minus 2 in positive form over here, over the same denominator. Okay. Now, aside from the fact that you might be going, why did we do that? Is it true? I mean, this did not change actually my original previous step, correct? It looks different, but it's the same value. However, I know now that this value is equal to 1. Yes? Yes, I do. Now I have 1 plus, and I've got 2 over n squared plus n minus 2. What happens if we let n go to infinity for the 2 over n squared plus n plus minus 2, what happens? It's going to go to 0, right? This is going to approach 0. It's going to approach 0. But is it going to approach 0 using positive values, or is it going to approach 0 using negative values? Positive. They're always positive on that particular one, at least far enough out towards the n values, right? Get a big enough n and we're good to go. It could be negative because of the minus 2 early on, potentially. I don't really care about that. I care about as we go to infinity. This is a positive value. So this is 0, but it's also greater than 0. It's doing it from a greater than 0 perspective. So I'd like for you to recognize that if I kind of ignore that expression, right? I'm treating it like it's going to 0, but before it actually, sort of gets there, the a sub n plus 1 over a sub n is now slightly bigger than 1, right? I took away something positive from the right-hand side, so now the left-hand side is slightly bigger than what's on the left on the right-hand side. I took something away. I'm ignoring that piece. It's bigger than 1. But if I multiply by the a sub n, what does it now say? It's pretty nifty, right? Ooh, I have an inequality. The inequality actually says that the a sub n value, if you want to turn it around, is less than a sub n plus 1. Where what?
Where did it say that a sub n plus 1 is smaller?
Right here is bigger.
Yeah.
I switched my inequality around. I turned it around just so that it was in order.
Oh,
So, yeah, so is the sequence increasing or decreasing? What does that actually mean? It's actually increasing. So this is increasing, and that's great, but we really just cared whether it was monotonic. But increasing certainly says it's monotonic. It is monotonic. All right, I'm running out of space on this screen. Let me go to the next screen and get a couple other facts. Might need to flip back and forth for a moment here. So some observations. Clearly, when n equals 0, a sub n is equal to 0 over 2, which is 0, right? My a sub n was n minus 1 over n plus 1. Let me just jot that down here as reference. So if n is equal to 0, I didn't mean 0, that's a typo. I just copied it wrong from my notes, I should say 1. When n is equal to 1, there we go, a sub n is actually equal to 0, right? And it's increasing. So this is the lowest it's going to go. We know it's increasing from beyond that. So our sequence, I'll say it that way, is bounded below by 0 because it's increasing, right? It's increasing. This is a lower value. All right. So let's take a look at what happens if we compare n plus 1, or I'm sorry, n minus 1 over n plus 1. So if I take this one and I just remove the negative 1 on the top, it actually gets bigger, right? That's a true statement, yeah? I'm not subtracting 1. What happens if I remove the plus 1 from the denominator? Does it also get bigger? Yeah, because I'm dividing now by something smaller, right? You think about fractions going both directions, so this is getting bigger. But the cool thing is, what is n over n? 1. So it's bounded above by 1. Hence, it's also bounded. We talked last time, and just let me remind you, just because something is bounded does not make it monotonic, and just because something is monotonic does not make it bounded. Okay, those are not, either or things that you could actually have it go any of those directions. So there's 4 possibilities. Both happen, neither happen, or one of each. Yes, sir.
Now, does that have to do with anything about being strictly monotonic?
No, the strictly monotonic doesn't come into play here. As long as it's monotonic, it's non-increasing, it'll still hold. Yeah. We are going to talk about the monotonic and how it will help us to do some other things later, though. Yeah. All right, let's move on then into section 19.